Hello everyone, so in this video I would like to show you how the Z drift correction or slow scan correction works, and mostly I would like to explain to you what it is, because it's the only correction in the read parameters that is always by default active. And first of all, what is it? How can we define this correction? Well, if we use the question mark as for many parameters that you can see here, you can see a quick explanation in the user manual. So here it says the slow scan correction maintains the height difference between the write height and the surface. So it's I will say just one sentence, but it says it all, and I would like to show you more in detail with a couple of slides what this means and why this is needed. So when we write, here I have the slide that explains the tip quality measurements and observation. So basically when we write, we can accumulate some contaminations, or we can have some planting, and we can have also some thermal drifts. So this phenomena can alter the effective tip height. Therefore, the forward height that we have when one of these phenomena happen is that the forward height is not the forward height that we set from the software, because let's not forget that the forward height that we set here is a fixed value. So this is going to be kept for all the lines that we write. So all across this field, we want to use always the same forward height. So what happens if we have some contaminations or blunting or some thermal drift? Well, we have this Z drift correction. So basically, let's see here, in this case, we have a contamination when we start writing, and then we set this forward height, but then during the patterning, this contamination can break off, and this means that our tip height decreases, so the forward height increases. So we have to lower the Z piezo scanner in order to go back to our forward height. In this case, you can see also a SEM image of a tip before when it's contaminated and after it's cleaned during patterning, for example. And here I would like also to show you how this looks practically from the analysis whenever we are patterning and, for example, we have a cleaning event. So we can see that we start patterning with the first approach, and we have these specific values of adhesion length. Then at some point, we have a cleaning event where we lose 77 nanometers in estimated tip height. So we get rid of this material that was accumulated on the tip. So the tip height decreases, but by cleaning the tip, we also observe that the adhesion length is drastically reduced, because you see that this accumulation of materials also increase the diameter of the tip at its apex. After it is removed, the tip is cleaner and sharper also, and this is hopefully only silicon material. Well, here we can have some carbon contaminations, for example. So what we see is that at some point we have this cleaning event which causes an increase in the forward height. So we see this spike of forward height, but we compensate this spike by a Z drift correction. So we lower the cantilever by 92 nanometers, roughly 90 nanometers, to accommodate this increase of the forward height. And the same but opposite will happen in case we have a blunting of the tip. So if we have a blunting of the tip, then the tip height will decrease. So we will have to do the opposite movement of the piezo scanner. So I hope this can help in clearing out how the Z drift correction works. and why it's important when we pattern. In the end, we always deal with the complex thermochemical and mechanical system when patterning with the nanofraser and TSPL. So this correction is very important to allow us to have a consistent results when patterning. Thank you, and I hope this helps.